You are invited to imagine, discover, and explore by taking part in STEAMfest 2021, an online event starting January 30th that is free and open to the public. Explore scores of engaging hands-on activities in science, technology, engineering, arts, and mathematics, including science experiments, art projects, building challenges, outdoor adventures, and live stream events. This year, online activities have been created by students, parents, teachers, and a range of sponsor organizations, including NASA, Google, several popular YouTube creators, businesses, and a number of community organizations. Join us in this family-friendly celebration by sharing on social media and with family, friends, and coworkers, sponsoring or creating activities, and of course, register your children to participate as STEAM explorers.
Greetings, everybody. Welcome to the STEAMfest Live Control Center for the final live stream broadcast of STEAMfest 2021. My name is Lee Blakely, and I'll be your host tonight. We've had an amazing 3 weeks. From chemistry and physics labs to sports science to the James Webb Space Telescope, the Mars 2020 landing yesterday. And nobody is going to forget the How to Cook an Egg live stream with Mr. Egg. Remember to register at wsteamfest.org and log this event in your journal, and please consider liking and subscribing to our YouTube channel. And now we're ready to get started. This afternoon we have Mark Stahl, who is an engineer in Huntsville, Alabama at the NASA Marshall Space Flight Center in the Optical Systems Design and Fabrication branch, which provides manufacturing and testing of conventional and X-ray optics. His group has contributed significant components and expertise to numerous groundbreaking space observatories, including the Chandra X-ray Observatory, the High Resolution Coronal Imager, and the James Webb Space Telescope. First, Mark is going to take us on a behind-the-scene tour of several labs, and then we're going to have a question and answer session. So get your questions together. And with no further delay, we'll get this started.
Welcome, STEMfesters. My name is Mark Stahl, and I'm coming to you from my living room in Huntsville, Alabama. I am an engineer at NASA with the Marshall Space Flight Center. Today we're going to talk about optics and making optics and testing optics and doing a little bit of a virtual lab tour in some of the facilities that I work in. A little bit about myself before we get started. I've been with NASA for about 7 years now. I have a bachelor's in physics from Wittenberg University with minors in math and East Asian studies. I then went on to get a master's in electrical engineering from the University of Alabama in Huntsville. Critical to getting to where I am today was doing internships both in high school and college. I'm with an optics group that specializes in manufacturing X-ray telescopes. Before we go on the tour, let's talk about optics and telescopes. What is optics? Optics is much more than just playing with laser pointers. It is the study of all light. Chances are good you know somebody who wears glasses. It is optics that enables us to understand the interaction of light and our eyeballs and how we can correct our vision using glasses. My glasses bend light in just the right way to allow me to see. We do the same thing with telescopes, using mirrors and glass to redirect and magnify light to allow us to view objects that are either too dim or too far away to see with the naked eye alone. Light, or visible light, is only one part of the electromagnetic spectrum. Other parts of the electromagnetic spectrum you might be familiar with include radio waves, bringing music to your car, microwaves, cooking food in your kitchen, infrared radiation warming you from your fireplace, ultraviolet radiation giving you a tan from the sun, or even X-rays from your doctor. All these types of light can be focused, directed, measured, and studied to tell us new and interesting things about the universe. The difficulty with building X-ray telescopes is that, just like at your doctor's office, X-rays like to either go through things or be absorbed by things. Bending X-rays like we would normally do with glasses or other telescopes doesn't work. So we have to build specialty designed cylinders that we use to focus X-rays. The X-rays skip like a rock off a pond and focus on the backside of the cylinder. By nesting a whole bunch of these cylinders together, we can create an X-ray telescope. So, how do we do it? Let's go on a tour. Welcome to the diamond turning room. In order to make an X-ray shell, we first have to make a mandrel. Mandrels can be as small as this one, or hundreds and hundreds of pounds. A mandrel first starts out life as a hunk of aluminum, and then it's turned to a rough shape, and then it's plated in nickel. Once plated in nickel, it's put on a lathe. It could be a small, or for the really huge mandrels, it's this guy that's huge. This machine uses tools that are tipped with diamond to cut the mandrel to a very specific shape and smoothness. From there, we take them over to the polishing tent. After diamond turning, our mandrels come here to one of our polishing tents. Here we use various liquid polishing compounds to polish the surface down to a very, very smooth surface. It'll spend 4 hours in here and then go off to be measured, and if it's ready, then it moves on to plating. If it's not ready, it comes right back here for a couple more hours of polishing. Sometimes it can take tens of hours to get a mandrel ready for plating. Let's go check out the metrology station. In our metrology lab, we have a wide range of equipment to measure our mandrels. Depending on how big they are or what we want to measure, we use different pieces of equipment. For small pieces or very smooth surfaces, this white light interferometer is very good. We also have other pieces of equipment that will physically touch off with a mandrel to determine how big it is. Welcome to our shell plating facility. Let's recap. Somebody wants an X-ray shell. First, we've had to take a hunk of aluminum, turn it into a cylinder, nickel plate it, diamond turn it, polish it for tens of hours, iteratively do metrology on it, and then it makes it over to here. Big mandrels require big baths. Small mandrels require small baths. So now you have a very smooth mandrel and you want to make a shell. In this facility, we dip these shells into these large baths with different chemicals in them and grow a shell on it. Once we have the shell to the thickness we want, we then take them out of these baths and then we pop the shells off by cooling the mandrel. From there, we take these over to our clean room facilities and we assemble the actual telescope. Welcome to the X-ray and cryogenic test facility. In this clean room, we both assemble and test X-ray optics, among other optics. The chamber I am leaving is about 75 feet deep and 25 feet in diameter, and we can test some pretty big optics. You may have seen the iconic image from JWST before. This vacuum chamber is used to simulate both the vacuum and the temperature of outer space. Parts of the chamber can get as low as minus 425 degrees Fahrenheit. Testing like this is very important to make sure that the experiments will actually work once they get to outer space. To test X-rays, we actually have a building about a third of a mile away where X-rays are generated, and then they're shot down a long tube to get to the back of this chamber. That long tube is critical to make sure that those X-rays look and act like what you would expect to see in outer space. I hope you enjoyed the tour today and that you enjoyed seeing what I do at NASA from day to day. Maybe one day I'll see you at NASA too.
And on that note, we'll hand this over to Mark. Mark, that was fascinating.
Thank you.
So we've got a couple of questions already. We're going to start with my question. I'm the host, so I get a priority.
Why not?
I noticed in the video that the mandrels are turned on a lathe, but then the shells are created by depositing material, not by machining.
Yeah. Well, actually, I have the shell that I had in the video right here. And so this guy was stuck on the lathe and he was turned to his specific size. And then we did all the polishing and all the other processing on it. And it's what they do is they hook it up. They actually use electricity and chemicals. So it's a electrical process as well. And they actually grow this shell onto the mandrel. And the benefit of doing that is that it enables us to make multiple shells from one mandrel. So we can do that over and over versus having to make a shell every single time.
Interesting. So I've got a question from Lily. She wants to know, in a typical antenna that you build, how many shells are there?
So I guess I have this picture behind us. And this is actually quite a lot of shells. I don't know the exact number in here, but we'll say 20 for the sake of argument. This might be considered a lot for the system, but it really comes down to its collecting aperture do you want. So how much light, because each shell is only collecting light around its edge because where the light is skipping off the shell. So it's not the entire area. So some telescopes might only have 4 shells because that's as much light as they need. This one, they needed a lot of light. Some build systems that have, maybe 20 of these. So it depends on how much you need. So you could be looking at 4 shells, or you could be looking at 400 shells.
The spacing of the shells, the concentric spacing of the shells and the diameter of the shells, is that related to the wavelengths that you're collecting?
The wavelength is dependent on how smooth. So since X-rays have a very short wavelength, you need a very smooth surface. The diameter and the spacing is all dependent on just how much light you want to collect. So if you need to cram a lot of shells in a small space, then you need to get that spacing tighter. You don't need as much light and you have more room. You might give yourself a little more space because it's going to be easier to make that way. If you look at, JWST, their surfaces are only to the nanometers. So their surfaces are maybe 100 times rougher than ours because they're looking at infrared light versus ours have to be 100 times smoother X-rays.
Okay, so in similar, if I'm understanding this correctly, similar to the way when you want to collect more optical light, you build a telescope with a larger mirror.
Yep.
With your X-ray telescope, if you want to collect more X-rays, you have larger and more shells.
Yep, that's exactly right.
Interesting. Okay. So we had a another question um, about okay. In your video, you showed like a facility that had a long pipe running into the test chamber.
Mm-hmm.
And I think that was there's an X-ray generator. What is the X-ray generator? How's that accomplished?
I don't actually know, but if I was to take a guess, I think they use electricity, and so they're generating those X-rays via some sort of electrical process, but they're doing it in a vacuum chamber, which makes it a little more complicated. The reason the tube has to be so long is because you want we call it columnized light. What that means is that all the light beams are parallel. Think about, a light bulb in your room, it turns on and that light goes everywhere. But if you move that light bulb really, 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 really far away, it's going to look like all that light is coming from that one point in the sky. It's called a point source. So the sun is really far away, and all that light, by the time it gets to us, is parallel. So we're trying to artificially do that with a really long tube.
Are the X-rays that you're working with, are they dangerous?
They can be dangerous, yeah. In one of our chambers, we have a very large wall of lead that we can roll around so we can hide behind it or block the source. But most of the time when the chamber is closed, all those X-rays are stuck inside of the chamber. They don't escape.
My brain was just churning on how you generate X-rays, and I see like they have a really big microwave.
Yeah, that's something like that.
That's the wrong kind of wave, though, isn't it?
Yeah, those are called magnetrons for
Okay.
microwaves.
Let's see if I can ask a question that doesn't involve me mixing up microwaves and X-rays. In the introduction, I stated that your group worked on the Chandra X-ray Observatory and the James Webb Space Telescope. Can you give us an idea of what role the group played, how they participated in those projects?
So for Chandra, we facilitated actually making the shells, and I believe Chandra. We didn't follow this mandrel process, so there were no mandrels for Chandra. We directly manufactured these shells out of glass. And so the reason for that was because the technology for this at the time of Chandra was not developed to the point of flying yet. By the time something makes it to outer space, you want to make sure that technology is well proven. So everything that gets to space is generally like 15, 20 years behind of the curve of ground technology. So for Chandra, this was made out of glass, and we manufactured it by polishing the inside surface. For JWST, our involvement there was more in the testing side of things. So moving those mirrors into our facility and making sure that they're the correct prescription, and then when they're brought down to temperature, that prescription didn't change, or it changed in such a way that was predictable and correct. So for there, we didn't manufacture anything, but we were involved in the testing of things.
Excellent. Looping back to that, to the idea that Chandra was glass instead of metal. I guess the X-rays are short enough wavelength to not care whether it's glass or metal in order to reflect?
Yeah, so since it's not going through the object, it's bouncing off the object. So it's really about a smoothness. And so, as a something to look up would be, it's called an angstrom. So we're polishing down to angstroms, and the angstrom is about the size of a hydrogen atom. So we're polishing surfaces to the smoothness of like 3 to 5 angstroms. So think 3 or 5 atoms of hydrogen next to each other. One thing I recommend to go online and look at the size of the universe. And it's a really fun little app where you can slide around the scale to see how big things are on the scientific notation scale.
Yeah, that's actually a really cool site, and we'll get that posted in the chat. And you actually answered one of the other questions about how much polishing or how precise was the polishing. Okay, I'll have to confess this next question is mine. Once you've polished, how do you determine that you've been successful in that polishing?
So there's two parts of polishing. One we call figure, and that's sort of the gross shape of something. Not gross as in disgusting, but gross as in the totality of something. And so, I'll just grab something random I have next to me. So this is a mason jar that's been painted. And so the bottom of this jar has, a concavity. So that's called figure because we want it to look like that. But then the surface roughness on this is paint. So this is very, very, very rough. So the question with polishing is to smooth without destroying the shape of the bottom. And so when we're polishing, a lot of what we're doing is we're trying to polish in such a way that we're not destroying the figure, the shape that's already there. And so we have to measure both for figure, that shape, and then we have to look at it on a small scale with like that white light interferometer that I showed in the video. And that will give us very, very localized measurements. And so we measure, on something this big, we might make 60 measurements all over the mandrel to say that, yes, we've polished the entire thing to, 5 angstroms, but it may be shaped like a banana, but the measurement of angstrom level measurement doesn't care that it looks like a banana, but the banana's bad. You don't want a banana.
It'll be a very smooth banana.
It'll be a very smooth banana.
So if I understand that, you're dealing with a couple of different issues there. If you, for example, polish too much on one particular side, then you'll no longer have the perfect cylinder.
Yeah.
And
I guess my one comment is it's not actually a cylinder. I don't know what's visible here. And so it's actually two different shapes. On one side of this, it's a hyperboloid, and on the other part, it's a paraboloid. And the combination of those two surfaces allow the X-rays to actually skip off this twice. They come in on one end, they skip off one side, then they skip off the other side, and then they focus on the back. So it's a cylinder for ease of conversation, but there's actually a little more complicated shaping to it.
We've talked about the diameter, but it sounds like the length of the shell is significant also.
The length is not as important as the diameter, but it certainly comes into play when you're trying to align a whole bunch of shells together. Typically, we grow them a little longer than this, and then we cut them off to give them a nice clean edge because the growing process makes it a little messy. And the reason I have this one is because it wasn't good enough, and so we had to get rid of this one, and it wasn't good enough to be used, and so I get to hold it and have it.
I'm not sure if anybody else noticed, but when you hold that up to the camera, it has an interesting effect on the light. It's I don't know, some kind of kaleidoscope of your face.
Yeah, so like looking at my teeth, you can see them in multiple directions, and that's because I'm putting my face about where that focal point is, and so the light coming off of my face is bouncing off the various sides of that mandrel, and then coming out the end parallel into the camera.
Another question. Okay. JWST is hopefully going to launch sometime in the near future.
Hopefully.
And Chandra is almost history at this point. What's next? What's your group working on now?
We actually build a lot of little things that you never really know. We do a lot of balloon missions. So these are smaller telescopes about this size that they get launched up in a balloon, and they spend a couple of hours up there, do their science, and then they're done. Those are cheaper to do than launching things into space, but you get yourself high enough in the atmosphere that you can get good science in. Other things we build are for neutrons, so not necessarily X-rays, but you can use the same processes and the same technology to develop mandrels for neutrons. So we build things for the National Institute of Standards and Technology, NIST, because they're doing research on that kind of stuff.
Sure.
So we have a lot of little small projects that we're constantly working on, but the big names like Chandra and JWST, James Webb, those things only come around every 10, 20 years. So we don't have any big projects on our horizon, but we're always chasing little science missions here and there.
How about does your group end up working with industry?
So
businesses, or can I pay you to build me an X-ray telescope?
yeah, so the role of government is to do things that are either too expensive or not economically viable for industry. So we're not going to make glasses because there are tons of people who can easily make glasses and make money making glasses. That's not our role as the government. Our role is to invest taxpayer money to do things that industry won't do because there's no money in it for them. And so, building X-ray telescopes, we're one of two places in the world that does this, one other being in Italy. So we're the only place in the US that does this. And, there's a couple of people who will make shells, but they don't make mandrels. And so they have to come to us to make mandrels for them. And then we give them the mandrels, and then they make their own shells. But so that's sort of the role of government and our lab, is we're filling this science need. Science is this interesting thing that, is there money in science? Well, should there be money in science? And so what our goal is to further our understanding of the world by doing something that it's not worth industry doing.
Well, I appreciate you pointing that out, because I think that's an important thing for everybody to understand. Looping back around to sort of future projects and future directions, are there particular like technological limits or barriers that you're working from, say, a research viewpoint to we can't polish a mandrel any further than this level, therefore we're thinking about some totally new approach, glass to a mandrel type?
Yeah, there's lots of competing technologies. Some people, they decide that making the entire shell is too hard, so they'll only make parts of the shell, and then they'll build holding structures to facsimilate a shell that way. And the rationalization there is, it's cheaper and easier to make small segments than it is to make the whole shell. You're always looking at weight, and so part of the reason that we don't make them out of glass anymore is because shells made out of metal are thinner, and weight is money when you're shooting things into space. One thing we're spending a lot of time and energy on right now is actually, CNC, computer guided machining. So these mandrels, you can get the idea that they take a lot of time to make. And so if we can add computers into the process to sort of accelerate or alleviate some of the time and manpower involved in these, we can make them cheaper, which then we can offer these manufacturing services to more science. So we can improve our understanding by improving our processes. And so that's where we're spending a lot of our time, is improving the process we already have.
Excellent. And in bringing us to a close, is there anything you'd like to add that we haven't covered?
Well, I guess for starters, I'm not a YouTuber, so I'm an engineer. So take my video with a little bit of sympathy. But beyond that, one thing I normally like to ask audiences of students is sort of what they want to do and why they're here, and I get answers sort of like, "Oh, I'm here because my teacher told me to be," or I'm interested in science and want to be a scientist, but I'm not sure what to do. So, my general advice to the world, or to the world of students, is, do what you're interested in. And if that's science, it doesn't matter necessarily if you're doing physics or electrical engineering or aerospace or chemistry. Having a good foundation in science in general can get you anywhere. And so in our NASA group, we have chemists, we have machinists, we have electrical engineers, we have aerospace. We have people all over the spectrum, from degrees of, not a college degree from an undergrad perspective, but a technical degree. And then we have PhDs, and I'm not a PhD. And so it's really just, if you're interested in science, go for it. And then if you're interested in being a YouTuber, or being a musician, or being a basketball player, fine, great, wonderful, pursue that. But I also recommend having a backup plan, because at least in the town I'm in, you have a much, much, much higher probability of becoming an engineer or something associated with that than becoming a football player. So, have a backup plan. That's my recommendation.
Mark, I appreciate that. It's always good to have a backup plan. Well, I want to thank you for taking your valuable time with us, both this afternoon and in preparing the video over the last couple of days to get ready for this. I think a lot of people are going to enjoy watching it over the next months or years on YouTube. For our audience, I want to remind everybody to register at wsteamfest.org. and like or subscribe to our YouTube channel. And this is the STEAMfest Live Control Center signing off.